All right, so we are going to continue with our lectures on building the Weyl tensor, and this is a difficult process. We have two choices when we talk about building the Weyl tensor. We can think about the Weyl tensor as the traceless part of the Riemann tensor, traceless part of Riemann mu nu alpha beta, or we can think of it as the conformally invariant part. Conformally invariant part of the Riemann tensor. And they both give us the same answer, right? They both give us the same answer, but they're totally different in technique, right? If I want to look at this and calculate the part that's traceless, that's actually not so hard. Calculating the part that's conformally invariant is relatively difficult, and we're going to do this one, the relatively difficult one, which I think is when people or when books do, and they rarely do, it's rarely actually will you see anybody construct the Weyl tensor in an elementary or intermediate textbook. In fact, it'll never happen in an elementary textbook and probably won't happen in an intermediate book. It's actually, this is rarely shown because it's kind of hard, but we are going to do this one because the conformally invariant nature of the Weyl tensor is actually the more important fact. The tracelessness is certainly interesting. The question is, well, if it's traceless and conformally invariant, there's probably a relationship between those two concepts. And I think there is. We'll show that relationship later after we do this proof. We may even do this proof. This proof isn't nearly as hard, but it will still take a lesson. But anyway, we're going to continue to work on this part, which we started in our last lecture. And just as a reminder, the conformal transformation is of the metric. So the conformally transformed metric, which is given by this hat, is the regular metric multiplied by some function on space-time, which is written as e to the pi of x. And the e factor there is to keep everything positive. So, x can contain a logarithm. So this can be a pretty arbitrary factor in front of this. But this is a function of space-time, and of course the metric components are a function of space-time. The metric tensor, of course, is written in my obsessive notation this way, including the basis vector of the space. If we're dealing with an infinitesimal transformation, which is what we're going to do, we write this conformal transformation in this way, and the inverse metric, we write it in this way. And the variation of the metric under this conformal transformation is epsilon pi, a factor of epsilon pi, where epsilon is a small number. And the variation in the inverse metric is minus epsilon pi. And we took those facts, we took these facts and our definition of the connection, alpha, beta, mu, and we calculated alpha, beta, the transformation of the connection under an infinitesimal conformal transformation. And we subtracted from it the untransformed metric, and that is the variation in the connection. I'm sorry, we subtracted from the transformed connection, we subtracted the untransformed connection to get the variation in the connection, which is what this expression was. And if you looked at this expression, you have your little epsilon factor out in front. You have the first derivatives of this conformal function. I'll call this the conformal transformation function or something like that. Maybe just the conformal function. The first derivative of the conformal function is a partial derivative. These delta functions here, the metric, and then this is also the first derivative of the conformal function, but it's with a raised index. So you might think of it as pi alpha, like that, where the line always stays down. I don't think anybody puts the line up there, but so it's raised derivatives like this. But the definition of this guy, regardless of the notation, is always going to be pi, one line, beta, g, alpha, beta, right? So you're just raising this index. And because this is a function on the space-time, the covariant derivative with respect to beta equals just the partial derivative for functions on the space-time. But once you take that partial derivative, this guy, of course, is a 0-1 tensor. And so now you can take its covariant derivative, right, with, say, some other index. And that will involve the whole full covariant derivatives definition. Anyway, we calculated this last lesson. We went to all the trouble of actually calculating that guy. And it was kind of a pain in the butt. But the good news is that we know that the Riemann tensor and the Ricci tensor and the Riemann scalar, those guys are all derived from this guy, which is all derived from the connections, right? The connection, which is all derived ultimately from the metric, right? And so if we know the variation in the connection, we can definitely calculate the variation in these three. That's the part I'm not going to do, because those are kind of long calculations and there's really not much to it, right? You just take this variation and you're going to calculate, in turn, you're going to calculate r hat mu nu alpha beta minus r mu nu alpha beta. With this guy is you use the standard definition of the Riemann tensor in terms of the metric, but everywhere you see the metric, you plug in the transform metric, right? So everywhere the metric appears in the connection, you use this expression or this expression as appropriate. And they both show up in there, right? And then once you've done that, you've calculated r hat, you subtract away r, and what's left over is this piece right here. What's left over will be the variation of r mu nu alpha beta. And I've done that over here, right? So this is the variation of r mu nu alpha beta, and you end up with this expression. Now you have second covariant derivatives, right? And second covariant derivative of a function is going to actually be the first covariant derivative followed by the second covariant derivative. You might see this notation for pi double covariant derivative beta nu. And I went through that in the last lecture about how those are the same. And by the way, it's also true that because of the symmetry of the connection, this object beta nu is actually equal to pi nu beta, right? That helps with these. If you're going to do these calculations yourself, that helps. Anyway, so you end up with these metrics, and these guys are, notice it's a 0-4 tensor, right? You've got epsilon pi and the regular Riemann tensor, and then you have this object here is a 0-4 tensor. And all these objects are 0-4 tensor, which of course is required. The variation of a 0-4 tensor has to itself be a 0-4 tensor. If you were to blow this up in the notation we use, that follows with the that keeps the basis vectors in place, what would you get? Let me write that down. Well, the first thing you would get is this here. This is just the component form, but what it really represents is the tensor product of the metric tensor, which is a field, right? Because this is a function on space-time, and the tensor represented by the second covariant derivative of this function pi, which is this tensor here. And and because of linearity, this comes out and this comes out to give you this product in front, and then you just have a string of 4 dx mu, dx alpha, tensor product, dx beta, dx nu. That's what this is the component of, right? I'd like to walk that through just to bring everybody back to this sort of vector basis theory. But anyway, that's the variation in the Riemann tensor, or the 0-4 version of the Riemann tensor. And likewise, you can calculate the variation of the Ricci tensor, and you get this guy. And here you also have second derivatives, which makes perfect sense. This guy here is just the sum of various components of that guy. So it really should be structured the same. But to get rid of two of the indices, you have a full contraction here. You see, this is G rho sigma rho sigma. So that contraction, so this object right here is just a function, right? That's a 0 rank tensor right there. So all you're left with is these two guys here. And notice that these variations are all in terms of the metric and pi. And then you end up with n here. N is the number of dimensions. Sometimes my n's look like news, so that's not good. Those are n. So n is the number of dimensions. And the way that shows up is because g alpha beta, that equals the number of dimensions. The fully contracted metric tensor ends up equaling the number of dimensions. So obviously somewhere in the middle of this calculation, of calculating this variation, you end up with an expression or two that look like this. And that's how these n's started to appear. And then ultimately, the variation of the scalar curvature, everything goes away, right? This is fully contracted. That's a real number. That's a real number. This is a real number. Those are real numbers. So that's a zero rank tensor. So with these three objects now, I should be able to figure out a way to calculate the Weyl tensor. So what's our next step? With these in mind, now we understand how variation works. And we understand how the variation of the conformal transformation works on the primary objects of our space-time, which is the metric itself, of course, the connection. The value of understanding it with respect to the connection was to give us these variations. So now we know how everything varies on the space-time. Now we can start intelligently talk about, and there's nothing else, right? These are the only things we know about. These are created by geodesics, which are created by the connection, which are created by the metric. There's no other fundamental tensors associated with our space-time that we know about yet, or that we've thought about. So ultimately, we know that the Weyl tensor is going to be constructed from these guys. We're just looking for a construction of that takes the Riemann tensor, the Ricci tensor, and the scalar, and puts them together in a way that's conformally invariant. So we're going to now that we know how those things vary, we have a fighting chance of figuring out how to find a conformally invariant part. But you can kind of see it's going to be a mess, right? How do I find a combination of these things such that these variations are all going to end up canceling? But that is what we're going to do. And yes, it is a pain in the butt. So we're going to, the decomposition that we seek is that the Riemann tensor is decomposed into the Weyl tensor, which is conformally invariant, and then some additional part that is not conformally invariant. Because we know that this guy overall is not invariant under conformal transformations, and we know that because we calculated it, and this is not zero, right? This could never be zero in full generality. So we know that this is not conformally invariant. So we're speculating that maybe there is a part of it that is, and then there's a part of it that isn't. And we're going to try to tease it apart and separate it. But what we're going to work with is actually the other way around. We're going to look for the conformally invariant part, and we're going to say that that equals the Riemann tensor combined with obviously some piece, say, subtracted away, although I do plan to use a plus sign here. So the logic we're going to use is actually this. And we're looking for some r hat, right, that will absorb all of the conformal transformation in r hat. Now, why are we doing this? Well, we're doing this because we're repeating the logic that I suppose Hermann Weyl used, because he was very interested in conformal invariance. That's just, to him, was a big deal. And his insight was good, and we're really just duplicating his process. So there's nothing super strict here. There's just certain kinds of logic that he used, and he went after it using this logic, and we're going to kind of duplicate his logic as best we can. So now we have to the problem comes down to constructing this piece. If we can construct this piece, then we've got it made, because we know what that is, and if we can construct this correctly, it will be designed in such a way that what's left over after these two are put together is giving us a conformally invariant tensor that is a decomposition of the Riemann tensor. So now the reasoning proceeds as follows. This guy here can only be built out of elementary things that we already know, which includes the metric, which includes the Riemann tensor, which includes the Ricci scalar, the Ricci tensor, and includes the scalar curvature. Those are the things, and I suppose you could say it includes the connection as well. But the connection is buried it's buried in the definitions of these various pieces. But ultimately, it's all built on the metric, right? Because the metric builds the connection builds the Riemann tensor, which builds the Ricci tensor, which builds the scalar. So everything's ultimately built off of the metric. So we can't use any other objects. These objects are what we're going to use to build this tensor. And then the other guiding principle is, for this decomposition to make sense, we know that everything has to have the same symmetries as the Riemann tensor has, right? Because remember, you write this with the Riemann tensor on, I guess I already erased it. Let me see if I can undo the erasure. Right, you write it back this way. This side has symmetries. Alpha, you flop alpha and beta, you get a negative sign. You swap mu and nu, you get a negative sign. You flip these two with those two, and you get it doesn't change, right? So these two things both have to share that symmetry. So this guy will have that symmetry by assumption, and this guy, when we construct it, will have to be constructed with that symmetry in mind. So now we have two principles. We've got to preserve the symmetry, and we've got to use just those guys that were mentioned before. We've got to use just these basic elements of the space-time. And with those two principles in mind, we're going to construct R. All right, so this is how we're going to proceed. We are going to construct our missing piece, or this part of I've rewritten the equation down below here. We're going to construct this thing out of the different combinations of the Ricci tensor with the tensor multipliers of some unknown tensors. But these unknown tensors, it's still understood, are going to have to be drawn from this list. And in fact, they're really just going to be drawn from the metric. So some functions of the metric are going to land out here. And there's also some 0,4 tensor multiplied by the Riemann scalar, the curvature scalar, that's also going to be part of this thing. So we've fulfilled our sort of obligation to just draw from this pool, right? The unknown tensors can contain G or possibly even these other things, but ultimately the construction really focuses on just the Ricci tensor and the scalar. The reason we leave this out is it's kind of already in there, right? This is, by definition, it's got a piece of the Riemann tensor as part of its definition. So what's left over from this list is really just these guys here and this guy here. And this guy's already sort of been used up a little bit, but anyway, this guy's just in terms of that guy anyway. So this is sort of the most general way of writing down what we want this to be. There may be other ideas out there, but this one is the one that actually works. So although the logic isn't 100% strict, I mean, I suppose something else could come out of nowhere and be an important part of this thing, but that's not the case. And when whoever invented this figured it all out, his analysis was correct. So again, we're duplicating his analysis. So this is under that assumption. So now we want this guy to have the correct symmetries. And the first symmetry we'll worry about is R mu nu alpha beta equals minus R mu nu beta alpha. So if we swap alpha and beta and alpha, we are expecting to get this negative sign to be introduced. And that has to happen for this tensor as well. So how would that work? Well, let's see. If we swapped beta and alpha here, beta with alpha, alpha with beta, what would end up happening? Well, this Ricci tensor term and this Ricci tensor term, which was normally different from this one, right? This was mu beta and mu alpha. Now it switches position. This is nu beta, and this becomes nu alpha. And all these other ones are different Ricci tensor terms, right? This is mu alpha, mu beta, which would become mu alpha and mu beta, and then alpha beta, they just switch places, and this one, it only affects this front term. So between these two terms, we have to introduce a full negative sign in order to preserve this symmetry. These other terms are also going to have their issues, but these for sure have to produce a full negative sign. This one will produce a full negative sign because we assume that W has the symmetries we need. We're forced into that assumption. So when alpha and beta are switched here, the negative sign should be automatic, and we have to keep an eye on that, make sure that this guy retains those negative signs. Okay, so but in order for this to work, right, when this is swapped, this guy has to come in as the same as this guy, but with a negative sign. So from that, we can conclude that alpha, or A mu alpha has to equal minus B mu alpha. And likewise, we would conclude from this that H mu alpha has to equal minus D mu alpha. So we can figure that out right away. We can also figure out that because, and this has a little bit to do with the fact that R is symmetric, right? Well, a lot to do with it. If you switch alpha and beta, right, here, which is what we're doing, we're switching alpha and beta, this term doesn't change at all. And there's nothing else out there to compensate for it. So E mu nu must equal 0. You do the same exercise on mu and nu, and you conclude that F alpha beta has to equal 0. So you know these two terms are gone right away. And so these symmetries are going to be forced to exist, and our answer had better include these symmetries, because without those symmetries, then our hat doesn't have the proper symmetry. So ultimately, we are going to start with a form of the our hat that is given by this expression right here. Now, all right, so now I'm going to write this back down in our full form where I've eliminated the two that are missing. I guess that was E and F, so they're gone. I'm leaving with A and B and H, and D like this. And now we're going to start working on this variation problem. So we know that the variation of the Weyl tensor, and the Weyl tensor, just like the Riemann tensor, is actually defined this way, right? Within the 1, 3 as a 1, 3 tensor. The variation of this guy has to equal 0. So now we need a condition. We need that this has to give us a condition that we can actually work with in the fully lower form, because we're operating in the lower form. And that's just because ultimately the algebra is a little bit easier. So we know that G, let's say a mu eta C mu nu alpha beta. Actually, why don't I do it this way? Why don't I put an eta up there like that? Right, that is going to equal C mu nu alpha beta, right? And but I know what G is, right? G is, we're now dealing with the transformed G, right? This is going to be G hat, right? So the point being that under the transformed in the transformed space, the lower form is going to be given by 1 plus epsilon pi G mu nu mu eta C eta nu alpha beta, right? And this is the regular G, right? That's the regular G, not the transformed G, which is just going to lower the index. So I get 1 plus epsilon pi C mu nu alpha beta. So this object here is equal to the transformed C mu nu alpha beta. It's just this factor of 1 plus epsilon pi, which is actually nice and simple. But now we want the variation in C mu nu alpha beta. See, we know the variation of this by our hypothesis is 0. But that does not mean the variation of this is going to be 0, right? We have to calculate the variation of that. Well, the variation of that is C hat mu nu alpha beta, the transformed conformal tensor, minus C mu nu alpha beta. But C hat, we've just calculated, is this thing. And if you subtract off the conformal tensor itself, the one term goes away, and all you're left with is epsilon pi. So this variation is going to be epsilon times pi C mu nu alpha beta. And that's important. The variation of C mu nu alpha beta is equal to epsilon pi C mu nu alpha beta. Right? So these two are equivalent statements, right? Just because the variation of the 1,3 form of the tensor is 0, which is what we're asking for, the variation of the 0,4 form of the tensor is not 0. It just pops out with a factor of epsilon pi in front. So we now have to calculate the variation of this guy, and it needs to end up equaling epsilon pi times itself, right? That's how this is going to work. So we're calculating now the variation of the 0,4 form, and we expect it to equal to epsilon pi times mu nu alpha beta, right? That is our assignment. That is our goal here. So the good thing about variations is the variation on this side is equal to the variation on this side, right? So the variation goes like this. Variations are very similar to derivatives. Now, this variation we know, right? Because we calculated it way back here. So we've already got one of the variations. So we're going to end up substituting this big mess right here, right in there when the time comes. What about these two? Well, the variation of alpha mu, or a mu alpha r nu beta, is just like a derivative. It's the variation of a mu alpha r nu beta plus a mu alpha times the variation of r nu beta. So this is undetermined, but this guy we know, again, because we have already calculated it right here, right? So we can slip that variation in very easily. And yes, that means we have to put in this whole statement here, which is a little smaller than this one at least. We have to put that whole statement here everywhere we see this. And we're going to get that statement in its various index forms for each of these terms. And then we have this last variation piece. But that last variation piece is going to have the same rule as this. The variation of omega w mu nu alpha beta times r is going to be the variation of w mu nu alpha beta times r plus w mu nu alpha beta times the variation in r. And again, we know this one from our work back here. And when I say our work, obviously it was the work done off screen that you can do yourself. And but this is unknown. So this is not known. These a's are still unknown, and the a's and b's are unknown, although we do have some relationship between the a's and b's based on the symmetry that we identified earlier. Okay, so what next? Oh boy, what next? Well, next is the messy job I just alluded to. We have to substitute that long term in here. We have to substitute that long messy term for all of these guys and for this guy. And we have to recreate this statement here without any variations, with all the variations in the known quantities substituted. So the variation of the Riemann tensor, the variations of the Ricci tensor, and the variation of the curvature scalar all have to be put in there. So let's begin. All right, here's the first part. Everything I just wrote down, right? This is all the variation of the Riemann tensor. That comes from this statement right here in the beginning. So if I did everything right, then this mess here is the same as this part right here. So that's just one piece of it. All right, now in green, I have put in the next part, which should be, if I did it right, it should be this piece right here, the variation of A mu alpha R nu beta, which I demonstrated here is the variation A mu alpha times R nu beta plus A mu alpha times the variation in R nu beta. And so here I've kind of reversed the order, but here's R nu beta variation A mu alpha, which is this piece. And then this piece is A mu alpha times the quantity variation R nu beta. Well, here's A mu alpha, and this is the variation of R nu beta. You'll notice that all of the other indices are fully contracted, so they go away. And you're just left with nu beta, and you have this. This is not a nu, this is an n. This is an n, the number of dimensions. And that expression came all the way from here, right? That came from right there. Epsilon over 2, g mu alpha, full contraction, n. Okay. So that is one of 4 terms that have to be identical. So let me write the other 3 now. All right, so this is the other 3. If I got all of the notation right, looks like I actually got this one wrong. This should be this one on the H should be mu beta here. See, it's not easy. It's not easy to get everything correct. Oops. This should be mu beta, right? Because all of these have to be the same. So the final index here is mu beta. These contract out, so this needs to be a mu beta to match that. There's mu alpha, nu alpha, nu alpha. So that's good. And this is, I have mu alpha, nu alpha. Okay, so everything else seems to be okay. So these are now all 4 of these variation terms of these guys that involve the Ricci tensor, right? So these are all variations of the Ricci tensor. So the last line we need is going to be the line involving the variation of this last tensor, this 0,4 tensor, right? And this will be mu nu alpha beta. And then in here, I need to put in, the final step is to put in this guy. And there we have it. So this is the complete thing. And this variation has to ultimately equal, I guess I'll put that down in black again. This ultimately has to equal epsilon pi c mu nu alpha beta, right? We know that that's the case because that's the version of this variation equaling 0 for the fully contracted, for the 0,4 tensor case, right? We did that little calculation. So the fact that the variation of the Weyl tensor is 0 implies the variation of the 0,4 version of the Weyl tensor is e pi times the Weyl tensor itself. Remember, this guy is the important one, right? When we derive the Riemann tensor, we derive it with an up index, and you're kind of stuck with that. And it's just the fact that we have a metric that allows us to lower the index. And in principle, we can derive the Riemann tensor without a metric as long as we know the connection. Once we have a metric, a special connection emerges, and then we have the metric so we can raise and lower indices. But this is the fundamental form of these things, with the 1,3 version is the fundamental sort of the original form. And that's the one whose variation we want to go to 0. So that implies this, which wasn't obvious, I don't think. But anyway, so now we have this guy, and we have to choose A, B, H, and D so that this is true. Now you may say, well, why don't I substitute our already existing symmetries for A and B here, and H and D? And we could have, but we're going to proceed this way and then find a more convenient time later to put those in. So what do we do now? Well, in the end, this has to equal the Weyl tensor times pi. All the derivatives of everything have to go away, right? So, for example, this derivative term here, the second derivative of pi, the second covariant derivative of the conformal function, that has to disappear. And the only way to make that disappear is to have pi beta nu cancel with pi nu beta here. And that's where the symmetry of this second covariant derivative is important, right? This guy is actually equal to that guy. So this term here is what we're going to have to use to cancel that term there. Likewise, to get rid of this term here, we're going to have to use this term here. And likewise with this one, we have to get, so we have to get these four terms to cancel with these four terms. And the way we do it is by choosing A, B, H, and D to make that happen. So let's just look at the first one, because they're all obviously going to be the same, up to a negative sign, right? Because here's a negative sign and a negative sign. So to cancel this guy, alpha nu with beta is going to be a negative sign difference than calculating. The procedure is going to involve one extra negative sign, then calculating, say, mu alpha or the beta nu, this guy, with A. But let's work on canceling this term with this term first. Okay, so I think I've written down the requirement correctly right here. This piece here has to cancel with this piece here, and that comes from this. We got to get rid of this second derivative, so epsilon over 2 g mu alpha beta nu, epsilon over 2 g mu alpha beta nu must cancel with a mu alpha epsilon n minus 2 over 2 pi nu beta, pi beta nu. So I've flipped beta nu already. So this guy has to equal 0. So that's not too tough. You just choose a mu alpha to make this all true. So what is that obvious choice? Well, if a mu alpha were equal to 1 over n minus 2 times g mu alpha, then what would happen? This n minus 2 would cancel there, and g mu alpha would come up front. So you would have g mu alpha times this, which would match that. And what's left over? Epsilon over 2. So this is our solution for a mu alpha, given the idea that we want this to cancel with this. So that forces, that cancellation forces this choice. Now there's a lot of other stuff floating around here that we have to worry about, but at least we've got a handle on this. Likewise with beta, you're going to get the same process, but you're going to get a negative sign, right? And you're going to get a negative sign here with H also, and then with D, you're going to get a positive sign again, because you have mu alpha, mu alpha. These two come in with a positive sign. So the A and the D come in with a positive sign, but the B and the H come in with a negative sign. So from all those analyses, you can get the, well, let's write down all of the answers. Oh, wait a minute. Yeah, I've already started screwing this up. In order for this to cancel, I've made the two terms the same, but in order for it to cancel, you need a negative sign here, right? In order to get, obviously, in order to get this piece to subtract from that piece to be 0, this has to be a negative. So now you'll end up with, this term will be exactly the negative of that term. So the negative sign gets introduced in the A, and then the B will end up being B mu beta equals 1 over n minus 2 g mu beta. And the reason there's no negative sign in this case is because here the negative sign nu alpha is already there, right? The negative sign is in this part. So that would translate to having a negative sign like right here. And if you had a negative sign right there, you wouldn't need it there, right? That's pretty obvious stuff. So, and then the other two are, okay, so there we have them. You know, the parentheses in the bottom, I'm putting the parentheses there, but obviously a fraction, right, kind of creates its own partitioning. But I'd like to throw the parentheses around downstairs like that. But ultimately, this is the solution for those three or those four coefficients. Now, from these, we can derive, if this has to happen, right? If you don't choose those, you won't get these cancellations. So these cancellations, getting rid of these four terms and these four terms, that forces what these values are. So right now we're stuck because, well, we still have W to worry about, but W isn't going to affect a lot of this stuff. Most of this is done, right? Because once we're forced what these are, we're going to be forced on these variations. So these terms are going to be what's left. And this all better add up to make this work, right? So let's proceed, right? So the variation of A mu alpha is going to simply be minus 1 over n minus 2 times the variation in G mu alpha. But we know the variation in G mu alpha is epsilon pi times G mu alpha, right? So that's the variation A. Then the variation in B mu beta is going to be similar. And so now we have all of our variations. So now these variations will get substituted. Will get substituted right in here, right in here. All right. So what is our next step? We're going to hold. We know that these guys here all cancel with those guys there. We now know the value of these guys, and we now know the value of these guys. So in principle, we should be substituting those values in and rewriting everything. Let's turn our attention before we do that to this term down here. Okay, so with this term down here, what are we going to do? We need to get rid of this, right? This is another second derivative. In fact, here we have a whole bunch of second derivatives. But the good news is that this second derivative and all of these are the same. These are fixed already in order to get rid of these guys, so we have to play with this cat in order for these terms to cancel all of these terms, right? So we got to get rid of all these derivatives because there's no derivative in the final answer. So now we have to choose W, this 0,4 tensor, to perform that exercise. So let's look at this. Well, this piece here is a 0,4 tensor, right? You've got this tensor product with that. This guy here is a scalar. This piece of it is a 0,2 tensor, but this is a tensor product. This is a 0,4 tensor. So if I take the sum of these four 0,4 tensors and add it to this 0,4 tensor, I better get 0, and I need to choose W so that happens. So let's write that down now. Okay, I think I've written this all down correctly. This term here is this piece right here, right? We don't have to worry about that part of it, but this piece, because remember, this is just a function. That completely, those are dummy indices. So that's a function, that's a number, that's a number. So this is all just a function times a 0,4 tensor. So that piece added to these four pieces is what I've written down right here. But we know what these guys are. We've calculated those guys. We calculated them right here. So I should now take all of these guys and substitute them right here. And what will happen? Well, these guys are essentially just a factor times the metric tensor, right? So it's mu alpha, mu beta, nu alpha, and nu beta times these factors with this sign. So this is just going to be G mu nu times wait a minute, that can't be right. Mu nu, you can't have these two mu's, right? That's not going to work. It's got to be mu alpha. This has to be nu beta. See, I can tell right away that's what this index notation is so good, right? G nu beta. Let's make sure the others are correct. Mu beta, mu alpha, mu beta, mu alpha. They're all the others are good. So this is going to be G mu nu times G. I'm sorry. This has got to be mu. I'm still screwing this up. This has to be G mu, not mu nu, mu alpha, right? Like that's where the problem is. The problem is up here. This is G mu alpha, and then this is going to be G nu beta, right? And that's correct. Yes, okay. So this is going to end up being replaced by G mu alpha, G nu beta, and then a bunch of factors. That'll be a factor, and this is, as we've been saying over and over again, that's just a function, right? It's fully contracted, so that's going to be a factor. And that's going to happen for all of these. So let's write down that final result. All right, let's see if we got this down. I made these substitutions. The substitutions are always going to be 1 over n minus 2, right? So there's the 1 over n minus 2. The epsilon over 2's will all come out. So there's the epsilon over 2. They'll all have this this fully contracted second covariant derivative of the conformal function. That comes out. So all that's left behind is the metric part of this unknown coefficient that we've established, multiplied by the metric term that's left, that comes from the original variation, right? This metric term here. And so that gives us these pairs, right? And then we have this guy up here. But remember, this has to all cancel, right? So this has to all equal 0. So given that it all equals 0, we have some common terms, right? This fully contracted function is in both this term and this other term that it's being subtracted from. And epsilon is in both terms. So we can actually dump that. So we can cancel. So that goes away, and that goes away, and that goes away, and that goes away. So that's pretty good. And then we can also use the fact that the metric is symmetric, right? So G mu beta, G nu alpha, G nu alpha, G mu beta. These are the same terms, right? And same here, mu alpha nu beta, mu alpha nu beta. So these two guys come together with an additional factor of 2, which will cancel with this factor of 2 down here. But I have to rewrite this as just G mu alpha G nu beta minus G mu beta G nu alpha, right? So in other words, you combine these together and I have a factor of 2 and a factor of 2, but that factor of 2 will cancel down here. So what's the final result for this thing? And this is my calculation for the final result. This tensor, if it, you get rid of all these terms, you end up with this expression, which equals 0, and then you just solve for this tensor, and you get this 0,4 rank tensor is just this combination of the tensor product of the metric. And that combination is actually pretty interesting. We'll talk about it maybe in one of our next lectures when we do the traceless version. And you have this factor of 1 over n minus 2 n minus 1. So we've solved for this. And the purpose of this now is that these terms are now all eliminated by virtue of this guy. These terms are all eliminated by virtue of our choice here. And now we're done with our choosing. Our choices are over. Oh, and by the way, you'll notice that the symmetries exist, right? This and this satisfy the symmetry that we required earlier, right? Where was that symmetry? This guy, right? A mu alpha minus B mu alpha, right? That's going to be true for this. You'll differ if you set this beta to alpha. You get these. Everything would be the same except a minus sign. So the symmetries are actually forced upon us already. So the symmetries are taken care of. So we're left with this guy. So now what's the deal? Well, these are all gone. All of these are gone. This is gone. So now you're left with this, this, and this piece right here. And when you add those things up, you have no freedom left. It better be equal to this, right? And so what we're saying is, if it's true that, if you got to go back to the chain of logic, I suppose, if it's true that the variation of the 0,4 version if it's true that this variation equals to 0, and it is constructed in this way, right? So I guess ultimately the point is our guess about how the construction worked. If that was correct, and we're going to demand this, then we've used up all our degrees of freedom, and the final result better be this. Otherwise, something's wrong, meaning that we've screwed up with the construction of the tensor in the first place, right? So magically, we're going to discover that this term here and all of these terms here that are left over, let me box the ones that are left over. This guy, this guy, this guy, this guy, this guy, this guy, and this guy, right? Those better add up to the Weyl tensor. Or those two better add up to this. All right, so let's see if they do. So this is that expression, right? The variation in the 0,4 version of the Weyl tensor has to be this term plus these terms that include the variation of those coefficients minus this term involving the 0,4 tensor W and the variation of 0,4 tensor W. So that all comes back from, here's the R times the variation of the 0,4 tensor W. Here's the 0,4 tensor W minus E pi R, right? That's this part and this part. And then all of these pieces are, and this piece here are these guys here and this one here. Okay, so now I substitute these variations in, right? Because we solve for A, B, H, and D, so the variations on those are forced on us. And I solve for W, and so its variation is forced on us. Although I don't think I wrote that down. The variation of W, right, is going to be the variation of this thing here. And each of these guys, it's going to be the same shtick, actually. It's, actually, you know what? We need to calculate the variation in W. Well, let's substitute everything first, and then we'll calculate the variation in W. So this is what you get when you substitute these variations in here. I did notice that kind of made a little mistake here, right? The variation, if B is this, the variation in B does not get that minus sign, right? And likewise for H, that minus sign doesn't appear. But the way to think about these variations here is that this actually equals E pi times A mu alpha, and this equals E epsilon pi times B mu beta, and this equals epsilon pi times H nu alpha. This equals epsilon pi times D nu beta, right? It's just, oops, there should be an epsilon pi here. So these variations are just a multiplicative factor of the original term, right? And there's this little epsilon to keep everything small, so that kind of makes sense. But that's very helpful because when you substitute for delta nu beta, you just substitute epsilon pi d nu beta. When you substitute for the variation of d nu beta, for example, you just get epsilon pi times d nu beta. And that's what we did here. Substitute for A mu alpha, you get epsilon pi times A mu alpha. Substitute for variation of B mu beta, you get epsilon pi times B mu beta. So all those terms are pretty easy. And then this last term here is very simple. It's just E pi R times this. But now we have to kind of look at the variation of W, which we would derive from this. And this is not too difficult to do either, because the, let's see if I can just do it in red, the variation of W here actually is going to be the variation of the right-hand side. You got a bunch of constants, and then you're dealing with the variation of just this term. And then this does the same kind of expansion that you get for any derivative. So you'll end up with the variation of G mu alpha times G nu beta plus G mu alpha times the variation of G nu beta minus the variation of G mu beta times G nu alpha minus the variation minus G mu beta times the variation of G nu alpha. And of course, the variation of GAB is just equal to epsilon pi times GAB. So each of these terms, you basically pull out an epsilon pi. Well, let me see, erase this. So you would end up with an epsilon pi times, and then you just basically get rid of all of these, and what's left is your answer, which combines in exactly the same way to form this again, right? So you end up with a factor of epsilon pi, right? So the variation, so in other words, you end up with an epsilon pi factor here, because remember, these guys will combine in exactly the same way they did when we shrunk it down from here to here. So the variation of with a factor of 2, but now there's no cancellation of the factor of 2. So you end up with, when you do combine it all, you end up with a factor of 2 there. So the answer ends up being the variation of omega mu nu alpha beta is 2 epsilon pi w mu nu alpha beta. Sometimes I say omega for w, but this is the variation in w, right? And so if I go back to here, I can take this part and I can rewrite it as minus r epsilon pi minus 2r epsilon pi, or is it plus 2? No, it's plus 2r epsilon pi omega mu nu alpha beta. It comes in with a, the variation term comes in with a plus sign. The term that's not a variation comes in with a minus sign. But this is the same expression, right? So you end up with just a plus right there, right? Okay, so that's fine. But now, look, you take this piece out, right? Take that piece, take the epsilon pi out, because, well, what do you have? Let me rewrite this. So now these two terms here have combined just to form this term, right? If I pull this epsilon pi out, so I have this whole expression here plus this expression here. They both share an epsilon pi. So I'm going to pull the epsilon pi out and bring this inside the expression, right? So how would I do that? I guess I would erase this, and I would erase that, and then I would redraw the bar like that. So what do I have inside? So now I have an epsilon pi here and an epsilon pi here. So now I'm going to pull that out and move the bar even further out, epsilon pi, like that. So now what's inside the bar? What's inside the bar is the Riemann tensor, and then A times the contraction, B times the contraction, H times the contraction, D times the contraction, and then R times this tensor. But remember, that was our assumed form, right? That was our assumed form for the Riemann tensor in the first place, right? That by definition was our Riemann tensor's assumed form. So the assumed form is actually shows up again down here. So what does this end up equaling? It ends up equaling epsilon pi times c mu nu alpha beta, which, by the way, is exactly what we were after, right? We were after this to be the case. So our assumed form was actually good. It was actually good. So now we know that our choices of A, B, H, D, and W do in fact get us to a point where we have created a conformally invariant Weyl tensor. And now we just put them all together and calculate. Now that we know our answer, we go back to, now that we know what A and B and H and D and W are, we substitute them in there, and now we have an expression for the Weyl tensor. And what is that expression? And based on our work, this is the expression. Now, we'll talk, I'm going to probably do a little mini lecture about the different ways of writing down this final result, because you can do a lot of different things with these minus signs and the symmetries. But this is a pretty common way of seeing it. Sometimes they'll fool around with a minus sign here, and they'll change some minus signs in here. But this is a pretty common way of seeing the Weyl tensor. And we now know that if we raise this index, we're definitely going to get C alpha nu alpha beta will equal 0. You will be able to show that if you actually raise the index and do the calculation, you will discover that that is true. Now, in a later lecture, I will derive the Weyl tensor by forcing that to be true, right? That's the alternative proof of what the Weyl tensor is. If you take the Weyl tensor as the traceless part of the Riemann tensor, then this becomes what you hunt for instead of conformally invariant. But we've proven that this is conformally invariant by construction, and this is ultimately the result of the calculation. Okay, so what we have done in this lecture is we have calculated the Weyl tensor using the fact that it was conformally invariant, and by demanding conformal invariance, we end up with this creature here. Next, we will do it by demanding tracelessness, and then ultimately we're going to tie the idea of tracelessness to conformal invariance and see what kind of insights we can get about the relationship between the two.